Now we introduce the core algorithm for this section, this lecture, which is the Bayes filter. And I'm going to write the algorithm in a form of a kind of a Python function. The algorithm is the Bayes, let's say, underscore filter, and it has 3 arguments. The first argument is the belief of where we are in the previous time instance, st minus 1, and this is evidently the posterior belief or posterior probability of what we are in the previous state. So what was our previous state was. And then the other one argument is this action that we take at this point in time, t, and the measurement zt. Okay, so these are the 3 arguments. And there is a kind of a for loop. We expect to see a for loop because, as we said, the discussion, the algorithm is going to be recursive. So for all STs, for all the states STs, first we are estimating the belief hat of that state because we are going to execute an action, and for that action that we are executing, we are effectively going to create a posterior that we will effectively integrate all the possibilities, almost like the convolution or sum rule. Okay, so let me write it down. This is st given st minus 1. This is my transitional model, if you remember from earlier, and this is the belief of st minus 1. This is the incoming belief where I believe I was before. And I use where sometimes in this discussion because in the back of my mind sometimes I have this simple localization kind of sort of use case, but please replace the where with what was my previous state. And okay, so that is basically the first formula. We'll actually draw it a little bit to see exactly what is going on a bit later. And then the second part of the algorithm is, now that I have the belief hat, I will do the so-called measurement update. This is also known as prediction step. And this is the measurement update step. The prediction step is kind of blind. We are not considering any measurement, and as we are just taking the action. And then the second step involves the measurement update. So it's a normalizing constant times p of zt given st times the belief hat of st, which we calculated over here. And then after we exit this kind of for loop, we are returning the belief of, let me write it as a return statement. The belief of st. It's also worth mentioning how similar, because it's exactly what's happening, this two lines is with the 2 probability rules that we have looked at the probability review video. So this one is very similar to the sum rule, and I'll write the sum rule in a moment. And this one is similar to the product rule, and we'll see how this is also obviously the product rule is associating itself with the very definition of the Bayes rule, and that's why we took the name of Bayes filter. And filter is a kind of a term that we have used extensively in electrical engineering to denote to actually call functions that are going to be receiving, if you like, a stream and are doing exactly the same job over and over again. Okay, so this is basically what's happening over there. So this function will be called now that we have the belief s of t. In the next iteration, this belief s of t will actually go here. Another action will be taken and a measurement will be received. And then the whole thing will repeat over and over again. That's the kind of recursive step. But coming back to this kind of two lines, the one and let me call it 1 and 2. The line 1, the prediction step is related to the sum rule or the marginalization, if you like, rule. And if you remember, the marginalization rule was p of x. Let me call this p of x. I used x and y variables when I was discussing these two foundational probability rules. So I said p of x is the sum over all y's of p of x comma y, or now that I can use also the product rule over there to expand this joint, is p of x given y times p of y. So replace the y with the state, no matter the index, and replace the x with I think you can replace the state with the belief on t minus 1, and this one with the state st. Okay, so then effectively you have what we have in equation 1 over here. Okay, so this the prediction step is related to the sum rule. Okay, and then the other comment is the that the measurement update is related to the product rule and to the base rule as follows. We know that the product rule was very much the p of x comma y is equal to p of x given y times p of y. We also know that p of y given x, comma x is equal to p of y given x times p of x. And so from these two, given the fact that p of x comma y is equal to p of y given x, we can actually conclude the very important kind of relationship that gives us the so-called posterior probability p of y given x is equal to p of x given y times the probability of y, which is called likelihood, times the prior divided by p of x. And actually we can write that as eta, where eta is associated with the normalizing factor 1 over p of x, which is sometimes very difficult to estimate, but in this case we will see that it's kind of straightforward for the case of the case that we will do in it has to do with a discrete version of this base filter, which is the first implementation we'll see in a moment, times a p of y of x given y times p of y. So here you actually can see that instead of an x, in this case we have the measurement z. Let me write it instead of z, the measurement. And instead of y, we have the state. So this is basically what we have in this kind of association between going from the first step and the second step to another recursion to update and find the next version of the state in the next time instant. Now, obviously, we need to see some kind of visualization of what's really happening to see why this kind of makes sense. And we'll have plenty of those in some kind of a Python notebooks in the simple single-dimensional case to see what is happening. But in the broad terms, let's say that I am in a room and I'm using now the localization kind of use case. Let's assume that I have some kind of furniture which I'm kind of aware of its coordinates, and I have, if you like, a robot, and let's say that is located right here in this cell, and makes a move. The moment that the robot makes a move, its location, without any measurement information, can be represented by some kind of probability distribution, okay, which is the posterior probability distribution. That is my belief hat. The moment I take an action, so this thing was induced, this transition was induced by this kind of action, and that gave rise to the belief hat. Obviously, I have some kind of estimate of some belief for, let's say, the ST minus 1. I have, this is my belief of ST. So a transition from ST minus 1 to ST. And as we will see, the uncertainty about the new state is growing in the absence of any measurement. And then what I do is the measurement is actually coming in, indicating, let's say, some measurement that kind of indicates how, in a proximity kind of sensor, how close is this kind of new location with respect to this object. And what will actually happen in the second kind of step, the uncertainty, there will be some correction, and maybe that correction will will be like this. So this will be my belief of ST. And this correction, as we will see, reduces the uncertainty associated with the new state. So we are, every time we are moving blind, as you can intuitively understand, in an environment, we are expanding in terms of my covariance of error that I see about my state, represented by this kind of bivariate contour diagram of this bivariate, let's say Gaussian. And then every time that I have a measurement, which I now do the correction step, the measurement update kind of step, that covariance sort of reduces. And the intuition behind it is that now that I have that additional kind of variable, what can I say more about that kind of posterior, okay? And definitely that kind of will reduce the uncertainty about my state, which in this case is a localization use case. So that is the whole story of what we will see, how this kind of filter operates. And we will see now that very clearly in the single dimensional case. So what we will do now next, we will first address two cases. One is the discrete case. And in the discrete case, we will see a robot trying to perform that kind of base filter. And then we will address the continuous case. And in the continuous case, we will be looking at Gaussian distributions to help us quantify the operation in that kind of space.